Since the emergence of 3D printing, engineers have found an enhanced ability to create specialized and complex parts. One new design selection that has come with 3D printing is the printing infill. A 3D printing infill is the internal structure a printed object has, consisting of material arranged in repeated patterns that partially fill the space inside of the print. Examples of infill patterns include rectilinear, honeycomb, concentric, and cubic. The selection of an infill can change the strength, flexibility, and mass of a part. The question is, what infills are good at resisting stress at different load conditions? The purpose of this project is to determine which infill pattern for 3D printing is strongest in tension and in bending. Due to budget and manpower restrictions, torque and compression loading conditions will not be tested. This experiment will cover the following instrumentation and measurement course topics: measurement standards, strain gauges, uncertainty analysis, normal distributions, student T distributions, and sensor calibration. We expect to see a correlation between the cross-sectional infill percentage and the yield strength of the test specimens. Additionally, we expect that more linear patterns will resist stresses better in tension, and more varied and perpendicularly set patterns will resist stresses better in bending. The focus of tensile testing will be to measure the load, stress, yield strength, and dimensions of each pattern. Tensile testing will be completed using the Tinius-Olson tensile testing machine, which measures the load with a resolution of 0.5% of the load. The machine is pre-calibrated, leaving only the test needed to be completed. The preliminary test follows the method we will use on all samples tested. A dog bone-shaped sample is 3D printed using PLA filament. The dimensions of the sample are then measured using a digital caliper with a resolution of 1/1000th of an inch. These dimensions are entered into the computer. The sample is loaded into the tensile testing machine, and the test commences. The load increases gradually until the sample splits. The data is recorded and saved for later use. The preliminary test worked perfectly, and is expected to be a robust system of measurement. By optimizing the size of the samples, there should be enough filament in the budget to use a significant number of samples, decreasing the precision error. Additionally, measuring the dimensions of each sample and following standard techniques for the tensile machine should mitigate bias errors. The focus of bending testing will be to measure the strain, bending angle, load at failure, and dimensions of each pattern. The yield strength will then be calculated. A strain gauge is bonded to a very flexible ruler, is wired to an amplifier, and then connected to a computer. The strain gauge amplifier system has a resolution at about 0.1% the expected strain. This system will help measure the strain of the samples without the need to attach a strain gauge to every sample. To minimize bias error, the strain gauges are calibrated against printed parts of known radii of curvature. This measurement can be used to find the strain and eventual stress of each sample. Once again, the preliminary test follows the method we will use on all samples tested. A beam sample is 3D printed using PLA. The dimensions of the sample are measured and recorded using the previously used digital calipers. The sample is fixed on one end, and a known standard of masses are placed on the other side. The center of mass of the masses are placed on the same position for every test. Masses are added in 50-gram increments until the beam breaks in bending. The preliminary test revealed some needed adjustment. No apparatus for holding the masses was used, and masses were balanced on top of the beam. Once the number of masses increased, the ability to steady the masses decreased. A bucket will be used in the future to refine this process. The mass of the bucket will be accounted for during testing. Additionally, there may be some bias error to account for. There may be a slight offset due to the ruler's resistance to the masses, although it is weak compared to the beam's resistance. Also, the calculation of strain using the strain gauge may have a slight offset due to the thickness of the ruler. Calibrating the strain to known standards of radii of curvature should mitigate this bias. Once again, several samples of each infill will be tested to decrease the precision error. By standardizing the test mechanics for each sample and measuring the dimensions for every sample, bias error can also be mitigated. It should be noted that for both tests, safety glasses were worn to prevent unlikely but potential injury to the eyes.